says it's doing. I don't know. Okay, let's do 6.5. Analyzing rational functions. This shouldn't be too hard. Continuous functions versus non-continuous function, which is a discontinuous function. It's something you actually, I think, learned a long, long time ago. Like when you were in elementary and first started doing graphs, they would have talked about continuous graphs and non-continuous graphs, all right? In Math 10C, we talk about discrete data versus continuous data. And so continuous is something that makes like a nice curve, right? A line that just goes and everything's connected. Discrete data like stopped. So what we're going to look at is continuous versus discontinuous, because it gets a little bit trickier now. Continuous means that it makes a perfect line, and at no point does it get like cut off. So you would never lift your pencil off. Nothing crazy. Most things we do are continuous. So you think about all of the equations we've done so far. Sinusoidal equations are continuous, right? It's just a nice line. And cosine graphs are continuous, right? Just a nice curved line. A quadratic, continuous. It's just a nice curved line. A linear equation, straight. But your pencil never comes off, so it's a nice straight line. If you look up here, they've drawn like a gajillion different continuous graphs all on top of each other. Almost everything we do is continuous. There are some graphs that are not continuous. Typically, rational expressions are not continuous. They're not continuous because of those asymptotes. Right? It makes you lift your pencil, draw an asymptote, and then do a next part of the graph. So if you look at these are all examples of non-continuous or discontinuous graphs. The one on the right, the furthest right, is probably the one we're most familiar with. That looks like our basic rational expression with asymptotes here and here. That would not be a continuous graph. Look how I would have to draw it, lift my pencil, draw it. Right? It's not all connected. Cool. The middle two, or I guess the left one and the middle one, are also examples of discontinuous graphs. They have something called what I refer to as a hole. So you go along the graph, and then there's a moment in time where that graph does not exist, and then it keeps going. So if you look at that first one, the graph is going. This open dot means that that part of the graph does not exist. And then it continues. This is not on the graph. An open circle, not on the graph. If it was closed, if it was bubbled in like this, then it would just be a point on the graph and it would exist, like anything else we've ever seen. So now we're going to have to start to look a little bit closer at graphs. If they mark a point, make sure it's a solid point. If it's a hole, if it's open, they're trying to say that that point does not exist on the graph. And it's discontinuous. So if you look at the next one, same thing's happening. So they have this nice function, it's going up, it curves down and up and over, and then it hits that hole, and then it keeps going. They are telling you that this spot does not exist. Right? There's nothing there. DNE does not exist. Cool. These holes happen in rational expressions. So they come from non-permissible values, things that, we've done these questions before in Math 1. We do a rational expression, we solve it, then we get an answer, it's like extraneous. We're like, oh wait, that was a non-permissible value. Right? It felt like I could have solved it, but for some reason that doesn't actually work. That'll create these holes and these like weird gaps in equations. So let's look. These holes are called points of discontinuity. I call them holes. I don't know. It's a hole. Yeah, but if you're looking for it, it's a point of discontinuity. The breaks in continuity can take two forms. We can get a vertical asymptote, which we are definitely aware of what a vertical asymptote is. We've done lots of those. And then you get these point of discontinuities, the holes in the function. To figure out if it's going to be a vertical asymptote or a hole comes from if you're dividing by 0 or not. So if we looked at something like this, f of x equals x plus b over x minus c, that thing would create a vertical asymptote. Right? You're not allowed to have x cannot equal c. This would be a vertical asymptote. That's like our standard question that we've seen lots of. Holes, or points of discontinuity, come from denominators. They come from NPVs, but then those NPVs can be simplified and kind of disappear. So, if you look at this question, that thing would still have an NPV of x cannot equal c. Agreed? If I put c in here, c minus c would be 0, can't have 0. So this is still a non-permissible value. That non-permissible value, though, does not create a vertical asymptote. The reason it doesn't is because if you reduced this rational expression, if you simplified it, the x minus c and the x minus c would cancel out. And this thing would simplify to just be x plus b. When it simplifies like this, I now have a linear equation that I could sketch, but that linear equation would have a hole because x cannot equal c. That's the difference between a hole and a vertical asymptote. Vertical asymptotes do not simplify. Holes simplify, and they go away. We'll look at some examples, and that will probably help. Let's look at this. And let's talk about holes and vertical asymptotes. Okay, look at this first guy. First thing I'm going to do is I'm going to write x cannot equal 2 or negative 3. Does everybody agree with that? Those are my non-permissible values. Perfect. These things are going to create holes or vertical asymptotes, depending on the question. If the NPV could be reduced, if it could be simplified and go away, it is a hole. If the NPV cannot be simplified and cannot be kind of canceled out, then it is a vertical asymptote. So looking at this problem, x minus 2 would divide by x minus 2. That would go away. And I would now have y equals 1 over x plus 3. This one is a hole, the plus 2. This one is a vertical asymptote, the minus 3. Because the minus 3 kept going, right? It didn't simplify out. It's still there. The plus 2 canceled out. It reduced. It went away. That means it creates a hole in my graph. I'm going to write it on the side here a little bit nicer. There is a vertical asymptote at x equals negative 3 and a point of discontinuity at x equals 2. I said at the beginning of the day, I was like, the concept's not that hard today. That's not bad, right? Yeah. If it simplifies out, we call it a whole. Otherwise, it's a vertical asymptote. Cool, this question did ask us to find the x-intercept. To find the x-intercept, we make y equals 0. So that means I have 0 equals 1 over x plus 3. I'm going to have to multiply this x plus 3 to the other side. Zero times anything, even 0 times x plus 3, is 0. So this is 0 equals 1. That doesn't make any kind of sense. There's no x-intercept on this graph. Zero times x plus 3 would still be 0. Right? So 0 equals 1. Doesn't make sense. No x-intercept. Cool, let's try a harder one. So looking at the graph on the right, if that said, like, determine the equation of the vertical asymptote. Looking at that, vertical asymptotes are non-permissible values. It's pretty hard to find the non-permissible value of that thing right now. The reason it's pretty hard is because this is a trinomial in the denominator. So trying to figure out what number would make that thing equal 0 is going to be very difficult. Last year, I used to write at the top of every question in this unit, factor. If I can factor, then I can find my NPVs pretty easy because it'll be binomials. This thing for sure factors. So the top factors to be x minus 3, x plus 3. The denominator multiplies to be x plus 5, x plus 3. And now I can find my NPVs very easily, and now I can go and create my vertical asymptotes or my holes. But I couldn't do that unless I factored. My NPVs are x cannot equal negative 5 or negative 3. Deciding if those are holes or vertical asymptotes comes from if you can reduce this or not. I can most definitely reduce this. The x plus 3's will simplify, leaving me with x minus 3 on the top, x plus 5 on the bottom. That means my minus 5 is a vertical asymptote. My negative 3 was a hole. Because the negative 3 got simplified. It went away. That one is now gone. That NPV would disappear, leaving me with a hole. My x plus 5 was still there. So my NPV of negative 5 is still there. That creates a vertical asymptote. If you want to find your x-intercept, which is what it asks you to do, you have to set y equals 0. Remember y, f of x, those are equivalent things, right? So that means I have 0 equals x minus 3 over x plus 5. I multiply x plus 5 to the other side, it's still just 0. So that means I have 0 equals x minus 3. Add 3 to the other side, my x-intercept is at 3. Three, comma, 0. Feeling good? Holes, asymptotes, math. All right. Let's do our calculators, I guess. When graphing, use zoom decimal or multiples of zoom decimal to see the point of discontinuity. Ooh, fancy. Let's try it. I don't know how I'm going to continue this video with a graph. I'll come back to this one so I can keep going with the video. Let's talk about horizontal asymptotes. Essentially, all we're going to do is we'll go back, we'll graph it on our graphing calculator, but I want to be able to show you, and then that'll look nicer, but I don't think I can keep doing that on here. And graphing is also not nearly as important as being able to do it algebraically, which you can do. Let's talk about horizontal asymptotes. I got there today. We were just talking about horizontal asymptotes and where that was, right? So our horizontal asymptote in the past had always been on the x-axis. We started to move it a little bit with some transformations, which was good. But sometimes you can't get into standard form, or sometimes it's really difficult to get into transformation form. So there is another way that you can find where your horizontal asymptote is going to be, or even if you have a horizontal asymptote. So we're going to look at equations where we have a function on the top and a function on the bottom. Okay, that's why they say p of x over q of x. Cool. We're going to check out the degrees of these functions. And we're going to compare numerator to denominator. And that is going to tell us information about our horizontal asymptote. First situation you're going to run into. You're going to get p of x is a smaller degree than q of x. So that means the numerator has a smaller degree. That's the first scenario that you're going to run into. I wrote pretty small. I didn't really have much room there. They give you an example of the numerator having a smaller degree. So look at this. I have x plus 2 divided by x squared. Denominator, that is a higher degree. It's degree 2. Numerator, degree 1. Right? Degree means highest exponent. Numerator is for sure smaller. Cool. If the numerator has a smaller degree, it's nice and simple. Your horizontal asymptote is at y equals 0, or the x-axis. That's what we would have saw last year. We always had functions with smaller degrees on the top versus the bottom. Every once in a while we didn't, but we just didn't let you graph those ones. So you never saw that it actually moved. Cool. Second scenario that you could run into. You could run into the degree of p of x and q of x are equal. That means that you have the same degree top and bottom. So numerator has the same degree as denominator. Something's wrong with my screen here. It's like disconnecting me. Right, like that's what this is saying. Same degree. They give you an example. If you look, the degree of this first one is x squared. Highest exponent is 2. The denominator, the highest exponent is y squared, so it's degree 2. These are equal degrees. When that happens, the horizontal asymptote will be the leading coefficients divided by each other. So looking at this, the leading coefficients would be 3 and 2. So the horizontal asymptote would equal 3 over 2. That's for when the degrees are the same. And the last scenario is when your numerator actually has a higher degree than your denominator. So they say P of x is greater than Q of x. I like to write that out using the words numerator and denominator. So numerator has larger degree. I think my screen's broken on this side of the Chromebook. Looks like I'm handwriting. I'm not. It's just my screen is very messed up. Looks like really bad handwriting. You know when you get like a letter from somebody who's like handwriting is just mush? Yeah, we all have that person? No. Yeah, some of us are like experiencing it. Yeah, some people like named Kylie do that. Yeah. Will was pointing at you. Just for the record. Just for the record. That's what my writing looks like with the board like breaking like that. If the degree is higher, there will be no horizontal asymptote at all. Okay, so it actually won't exist. Yeah.
Does this only apply when the equation's in general form? Because if it's in standard form.
If you could see it, yeah, this has to be in general form where everything's together. If you were in like transformation form, then you could just see the horizontal asymptote by the transformations. But if you aren't in your general form like this, then we can just do simple comparisons. So 3 scenarios. Basic one. Numerator is smaller degree. That thing will just be on the x-axis. Y equals 0. Doesn't move. This one is where their degrees are the same. You just take the leading coefficients and divide them. And the last case is when the numerator actually has a bigger degree. You're not going to get any horizontal asymptotes when the degree is larger on the top. It talks about a slant asymptote. I don't think we do that. No, we don't do that. So we're good. We don't need to worry about slant asymptotes. But it is kind of cool. That's a future problem. All right, look at that. We've made it. Last slide. Do you want to try these on your own? Get 10 minutes. I'll give you 5 minutes to try to do both questions. That's a little short. That's short on time. But give it your best go.